Hello, this is Dr. Rahi, and today we are going to see this chapter about the main memory, where we will be seeing the management related to memory, that how an operating system actually use the memory resources. By main memory, we mean to say that the primary memory, in which we have specifically we talk about the RAM memory, but there are also some other type of memories which belong to primary memory, such as registers and RAM and the cache. So these all three type of memories are actually primary storage, while these will be covered in this chapter also. Okay, so we will start chapter number 9, and here it is. So before going to see the chapter in depth, we will start from the background. What is the background of the memory management? We will see some common used concepts in this background, and then we will come to the core topics. And some of those topics are contiguous and non-contiguous memories. Just let me start this again. Okay, yeah, so we have two type of actually memories, the contiguous memory and the non-contiguous memory. So in contiguous memory we have actually this is a type of memory where we store all the process related information in the contiguous memory is actually a continuous type of memory. Okay, continuous type of memory allocation, right? In this type of memory allocation, what happens that whatever the process comes, it will be assigned the place in memory in continuous form. For suppose if we have a process here, and this process is only 3 locations long, 0, 1, 2, then if this will be moved to the main memory, then it will these locations 0, 1, 2 will be placed somewhere continuously. Now for 0, 1 and 2, right, somewhere these will be placed continuously. However, so there are many advantages and many disadvantages of this type of memory allocation. For suppose we have fast access, because RAM is actually far than cache or register. So for fast access from RAM, this is a good approach, but at the same time this is not sometimes this is very technical to deal such allocation, and there is also some memory space wastage also. So we will see the in depth and understand the contiguous memory allocation systems. We have also non-contiguous memory allocation, such as paging. Non-contiguous memory allocation. In this type of memory allocation, the same process is actually scattered in the different memory allocations, in the different memory location. For suppose 0 is here, 1 is here, maybe 2 is here, right? So we have the same process, but it is stored actually on different places. Now here we minimize, or we maybe overcome several disadvantages of this contiguous memory, but also we have some challenges. So we will see the non-contiguous memory, and the example of non-contiguous memory specifically we will see the paging here. Also, beside paging, we have another type of scheme of non-contiguous memory, that is segmentation, right? We may see some overview of segmentation also. However, this is not in your book. Okay, and then we'll see the page table. Actually, page table is the part of the paging scheme. So this is the very important concept when we are talking about the paging type of contiguous non-contiguous memory, right? And then in the end we will be seeing some I will introduce you about the sweeping. Now in this chapter we have skipped a few topics because now we have to wind up everything, so I might have skipped some topics from the chapter. However, I'm only covering the important topics here, right? So starting from the background, now we have actually a process is actually before becoming a process, it's a code, right? It's a code, and there might be some associated data with that code right here. Now this data is binded with the code, and that whole becomes a process when it is shifted to the main memory, right? So somewhere in the main memory, when this is allocated, it is called a process. Okay, so program must be brought from disk into the main memory and placed within a process for it to execute. Okay, now the CPU has direct access to only two type of memories for now. For basic understanding, we say that there is a CPU, okay, and then we have different type of memories at different level of access, right? Now here, very near to CPU, we have some memory, we call it as a register. Okay, after register we have cache here, we have cache memory, and we have the RAM here, right? RAM, we can also call it main memory. Okay, and then we have secondary storage here. Okay, secondary storage, maybe your hard drive, right? Now at different level of the storage, we have the speed, we vary in the speed of access. Now for suppose, if a CPU wants to access directly from the register, then we might only consume one CPU cycle. Okay, but if the CPU want to access from the main memory, then it might consume several CPU cycles to approach to the main memory. Now here, if we say that, for example, this wants to access from the this register, then it might only consume one CPU cycle, right? One CPU cycle at the time, right? And if it want to access the same data from maybe from main memory, then it might consume 1 and 2 and 3 and 4 and 5, maybe 4.5, right? 4.5 memory cycle, right? So as the distance grows, we have the slowest access from different type of memory. Similarly, if we want to access from secondary storage, then still we need some more cycles to get access from there. However, the CPU has direct access to some of however, the CPU has only direct access to register and the main memory. However, also the cache is there, but for now you just understand that a CPU has direct access to only the register here and the main memory. Okay, now register access is done in one CPU clock. As I have already told you that within one CPU clock you can access something which is residing inside the register memory, right? But if you are going to access from the main memory, then it might take several cycles, thus causing the stall. I have already told you that stall is actually a memory waiting for some input or output. This is what we have already seen in a previous lecture, right? So now whenever we are accessing something from main memory, then there is something we need some protection. For example, if there is a process, maybe here we have a process, right, and maybe P1, right, and this is 0 to 1000k, right? Let's say it's a 1000k process. Now inside the main memory, when it is loaded into the main memory, somewhere at the location, it can be located anywhere in the main memory. For suppose it's located here maybe from 3000 to 4000 location, right? Because the process is long for 1000, so from starting from 3000 and ending at the 4000. Now we must have some way to limit this access, because when CPU is accessing this process, then it might go beyond the limit. Now we have to control this access and for the performing the correct operation to ensure that whatever data we have accessed from the main memory, it is correct. So we have two parameters here. We have a base and the limit. Now base is when your storage starts over the physical memory. When we are talking about the main memory, the locations of the main memory are called as a physical memory. So in the physical memory, from where it start storing the data is called as a base location, and when it is finished or it is completed the storage, when the allocated space is occupied, when the process occupies the required space, and then it is called the end of the process. So end is limit and start is the base here. So we'll see this in detail here. Now we have the same example here, that for suppose if we have a process, maybe it is 1209, right, long. For suppose there is a process which is 1209 locations, maybe k size. This is the size of the process. So we might need 1209 locations in the main memory to store this. So this process is starting from 3040 and it is going to 42094, right? So the start location is base and the end location is the limit. Okay, when you add base and limit, then you will get the physical location. Physical address, sorry, location not, but it's the address, physical address in the main memory. Okay, so this is the main memory. Okay, so this is what the actually protection is from the access outside of the limit. So we protect a process to go beyond its limit by using these two parameters, limit and the base. Okay, now now talking about the hardware protection, a CPU must check every memory access generated in user mode to be sure it's between the base and limit for that user. Now for suppose here if we see that, let's say this is a 300, the logical address, actually the address generated from the CPU is called the logical address. Okay, and the address over the main memory is called the physical address, right? So when we are saying that for suppose this there is 300, right, is the logical address, or maybe 3000 is the logical address. For suppose if from 0 to 3000 we have operating system stored over the physical address or maybe the main memory, because whenever you push the on button or switch on button on your CPU, then an entire operating system or maybe the very critical or maybe some very required sources of operating system are loaded into the main memory. So at any instance of time we say that 3000 locations are already occupied by operating system 0 to 3000. Mostly the operating system is loaded in the higher level because it's the first thing loaded in the computers, and the user programs are loaded in the lower level of the memory. So for example 3000, the CPU has generated the new process is starting from 3000. Now what base will do, base will check that if this 3000 is less than the operating system limit, Now operating system limit starts operating system base is this and its limit is this. Now what will happen, that this will check that whatever the logical address generated by the CPU is actually greater or equal to this limit. Means it can be 3000, it can be 3100, but it should be greater or equal to this address, right? So yes, if yes, then it will go to further, and then it will see that it is actually less than limit. Now what's the limit here? Limit is actually base plus limit, right? Because we have already something in the physical memory. That's why the base of new process is starting from 3000, so we will add the base also here. Now for suppose if a process is 1200 bytes k maybe long, then the base is 3000, right? And we add these two, then we will get 4200, right? So what this base plus limit will check, that this process is up to the limit of 4200k locations, right? 4200 locations. Now this is where actually this process belong in the physical memory, right? Now if anywhere there's mismatch, for suppose this is maybe 2900 or maybe 1300, the logical address generated by CPU is, let's say, 1300 or maybe 2900 even, the error will be generated. This is an illegal addressing error. In both situation, if an error is generated, that is called an illegal addressing error. This is an operating system error, right? So we see that hardware allocation is also hardware protection is also provided like this. Okay, the instructions to loading the base and limit registers are privileged here. Okay, they are given preferences over here. Okay, so I hope you understand this. Then the next thing comes, actually we are now accumulating some nomenclature related to this chapter. So next thing is address binding. Address binding, what is an address binding? We have actually logical address and physical address. Okay, when we bind these two addresses together in a process, then that thing is called actually the address binding. Okay, for this I am going to give you some example. That for example, if we have a program here, and this program might have some data access over different locations, right? Now this is the program. Now this is a data to access, right? Now for suppose when this, now this might have location 1, and this might have location 2, this might have location 3, and this might have location 12, right? And this is the main memory. Now when this process wants to access, this process is executed, then what happens, that these all are bound into a new location. Let's say maybe we call it 15, right? Maybe sorry, 12 and 13 and 12, 15 and 3, maybe 18, right? 18. Now we have this whole thing bound in this one piece, right? And this is then moved to the physical location. So that's why we call it as logical address to physical address migration, right? Okay, so this is actually the address binding simply. Now there are three type of address binding. The first one is compile time binding, and the second one is load time binding, and the third one is execution time binding. I will be hovering over all these one by one because these are very important. Now first we come to the compile time binding. In compile time binding, what happens, that it is also called static binding. Right? is also called the static binding, because what happens that in this type of binding, when you compile a code, it is fixed to an absolute address. What happens that, for suppose I give you an example, that if you are going to travel using the train from maybe Sukkur to Karachi, then when you go for booking, then you know that what is the train name, what is the train timing, what is the bogie number, what is the seat number or berth number, either it's in the middle or it's in the upper portion or it's in the lower portion, the berth location, everything you know. So whenever you are going to depart for the train when you are going to the train, you already know this information that I have to go to the bogie number 8, maybe seat number 22, and somehow like something like that, timing and date, everything you know in before, so you don't need to search. Okay, the main advantage of this is it's very fast, and whenever you're compiling a code, the addresses are generated at the time of compilation, that where this will be stored over the physical memory, right? The address is generated in the advance. Address is generated on compile time. Compile time. Okay, so there is advantage is that we have minimum setup time, right? Because we don't need to find out anything. For example, if I go then I don't need to ask anybody, I don't need to ask from TT that where I should go, where's my bogie and this is my ticket, now please direct me. We don't do this while departing for the train, right? Similarly, when we are compiling a code and we have the binding, compile time binding, we have static are fixed variables, are fixed memory allocations already for that program, then we don't need to actually search. So the setup time is very minimum here. While the disadvantage is that, for example, if that location is already occupied by some program, then what will happen? There is actually a condition of collision. The disadvantage is collision, right? For suppose if something is already over there, this is the advantage and this is disadvantage. Okay, so something we call it collision. A collision is occurred and it overwrite the existing process. Okay, override the existing process. So we have one type of binding is called as a compile time. Then we have a load time binding. Now this is actually a binding which is a type of address binding when the up to the compilation up to the compile time the location is not assigned. Actually, when it is compiled, it's okay, it is compiled, but the locations are not actually allocated to that code, right, that program. But when once it is loaded into the main memory, then only it allocates all the required resources. Now maybe the good example for this is your Windows operating system. When you switch on your computer, everything is loaded into the computer. Now we know that once it's loaded, however this can be a compile time binding or maybe load time binding, but just for an example, everything is loaded in the higher level or maybe the lower level of the memory. So when sometimes the applications loaded inside the loading of application, that might shuffle the memory locations, but these are loaded in higher or lower level of your main memory. So we see that for example, I give you a simple example for this, is that for example, if you are going to book a flight, right, maybe from Sukkur to Karachi, or flying Sukkur to Islamabad or somewhere else, so you know exact time, you know exact date, you know exact flight number, you know everything else, except you don't know the gate number, the departure gate number. You know even which airport you are going to fly, you are taking to fly, right, from, but you don't know the gate number. Some information is missing over there, which is actually provided at the load time, right? For example, gate number, you don't know which gate number you will be departing. For example, seat number, if you are not booking seat, if you are not reserving seat, there's an exception. If you have already reserved, that might be possible, but these two things are usually not provided at the time you are actually reserving the ticket. So these two things are actually decided when you are getting boarding pass. Once you get the boarding pass, then you only know, okay, gate number is B2 and seat number is maybe 55A, right? Now you know that where you have to go, which gate should you should take for easy access to your flight, right, to your seat appropriately. So you don't need to ask from air hostess that where shall I go. You know exactly that, okay, 55A, that's my seat number, then I can go from this gate, okay, and this is the gate number you get. So these type of information are actually allocated at the runtime. That's why we call it as relocatable code. This means that the information, the code, or the maybe variables, or maybe the routines which are involved in the code are allocated the memory locations at the load time, right? That's why we call it as a relocatable, because it can be relocated. Okay, now I will give an example to you. For example, for relocatable, this is the main memory. Now we have 0, 1, 2, 3 up to maybe 8000 memory location in main memory, right? And here is the process, which is 0 to 1000 locations long, right? Now this location is actually the relocatable address of a program, relocatable address or code, and this is the base addresses. Now when you add these two, base and relocatable address, then you get the physical memory, physical address. Okay, now the third one is execution time binding. I hope you got this load time binding. It must be clear to you all, guys, right? Now the third one is execution time binding. Here what happens, that the location of a program in the main memory is decided at the runtime. Okay, at the runtime this decision is taken. Okay, now for suppose sometimes, but most of the time we call this as a dynamic linking, is also dynamic binding is also an alternate name for this. Dynamic binding, we will see dynamic linking, dynamic loading, and dynamic other related concepts of the dynamic memory allocation. So dynamic binding is the alternate name, also known as, this is also known as dynamic binding. Okay, so what I was saying, that okay, for example, I give you an example of this also. For example, if you are going from Sukkur to Hyderabad or maybe Karachi, and you don't know which bus or maybe when you are going to take for your journey, so you go from here and you find a van, you don't know, still you don't know that where you are going to sit, right? So this is actually a dynamic binding, that every decision is actually taken at the runtime, right? So this can be shuffled even during runtime. For example, if you are sitting, someone has come, sometimes they ask you to go beyond, or they ask you to go forward, right? So this shuffling can also happen in the execution time binding. What's the good thing about this? That unnecessary routines, unnecessary information is not loaded into the main memory, because we know that main memory is costly resource, costly in terms that we have limited resources of main memory. For suppose in your hard disk you might have 500 GB of tools installed in your hardware, but in the RAM you have only 16 GB or maybe 8 GB of RAM in your computer. So we have very limited resources. Now you cannot load all of the programs in your memory, right? But sometimes you load enough amount of programs in your, you can load enough amount of programs in your main memory. You can run several concurrent programs, right? For example, you are running operating system, it's itself a big program, maybe occupying 3-4 GBs of your RAM, and then you might be running let's say Maya or some graphic tools, right? That might be taking 2 or 3 GBs, and maybe you are running also MATLAB beside that's also taking some part of your RAM, and you are also running some games. So how this is actually done, that you can load maybe 50 GB applications in 16 GB RAM. This is actually done that only those modules which are in use are loaded into the main memory, while those modules which are not in use are not loaded into the main memory, so that we can efficiently use our costly resource of the main memory, right? Now we have seen that we have 3 type of bindings. The first one is compile time binding, second one is load time binding, and the third one is dynamic binding, also called as execution or runtime binding. So what happens when it's compile time binding? We have already seen that the code is actually assigned with the address of physical memory at the compile time. Before proceeding for the execution, the location of storage, the location of placing the code, the routines are actually well defined in prior, right? So this is what happens, that the compiler or assembler actually gets all the addresses over here, right? So this is actually general structure at the of a general flow of a program, that this is actually the compile time, right? Here everything, when we are saying it's compile time binding, then it means that all the libraries, all the other objects are actually linked over here at this time when we are saying it's compile time binding, right? When we say it's a load time binding, then what happens, that all the required routines and system libraries are actually loaded at this time, right? And when we are saying it's execution time, then this is happening actually, that system libraries and other objects are actually loaded when they are needed, right? Loaded when they are needed. So this is all we have already discussed in previous slide.